Hello, this is a pilot episode of a series called Stochastic Calculus for Absolute Beginners. As the name suggests, the prerequisites are kept at a minimum, just basic calculus and probability. If additional backgrounds in real analysis is called for, we will go over them along the way. Let me know in the comment if you're interested in the continuation of this series. Today we'll give a definition of the Ito integral, one of the central notions in stochastic calculus. Our focus is intuition building and visual understanding, rather than formal rigor. Software engineers say, get it working first and then optimize. My philosophy is similar. First obtain a working knowledge of a subject, then iron out and fill in the technicalities later. Let's go. To motivate our concept, let's consider a gambling sequence. A spirit true to the origin of probability theory. Let's play a game. At each step, toss a fair coin. In notation, for each I equals to 1, 2, and so on, let's denote delta Wi, a random variable, the outcome of the I's toss. That is, Wi's are IID random variables that takes two values, plus or minus 1, each with equal probability of 1/2. To make the game more interesting, before each coin toss, you place your stake xi minus 1, say in dollars. So, before the first toss, you place your stake of x0. Before the second toss, you place your stake of x1, and so on. If the I's outcome is 1, you win xi minus $1. If the outcome is minus 1, you lose the same amount of money. And here's a diagram. The key is that at each step, the stake is placed before the coin toss. So a natural question is how much money you win or lose after n steps. And the formula is quite straightforward. The wealth after the n step is yn equals to the sum of xi minus 1 times delta Wi, where I ranges from 1 to n. Basically, if you win the I step, xi minus 1 gets a positive sign, otherwise it gets a negative sign, and you just sum the whole thing up. And this is essentially the Ito integral in its discrete form. Our goal is to define stochastic integrals in continuous time, something that would look like yt equals to the integral from 0 to t, xs times dws, where t is continuous time. The meanings of the integral sign xs and dws are to be specified. But before doing so, we emphasize a key assumption in the stakes xi minus 1. It's called non-anticipation. Xi minus 1 can be almost any function. It can be deterministic or random. But it cannot rely on outcomes of future coin tosses. That would be cheating. Let's look at some common strategies, and we'll see that they all obey this assumption. First, we have the constant stake strategy, also known as buy and hold. The idea is to always bet the same amount. So xi minus 1 is a constant c. Next up, we have an interesting strategy historically called the martingale, or doubling. The idea is you start from the initial stake x0 of 1. If you lose, you double it. If you win, then reset the next stake to be 1 again. So imagine if you place $1 at the beginning, and it turned out that you lost the first round. So in the next round, you double the stake to $2. And if you still lose, you double it to $4, and so on. So the formula for xi minus 1 in this case is 2 raised to the power of li, where li is the length of the losing streak. So xi only depends on the latest consecutive number of losses. It does not depend on the future. Next up, we have the momentum strategy. The idea is to follow the previous outcome. The opposite to the momentum strategy is called the mean reversion strategy, in which you bet the opposite of the previous outcome. Xi minus 1 equals minus delta Wi minus 1. And lastly, we have the proportional wealth betting. The bet is proportional to the current wealth. Xi minus 1 equals alpha times yi minus 1, where alpha is a constant. If you're rich, you bet more. If you're poor, you bet less. And of course, this is by no means an exhaustive list of strategies. The point is, all of these strategies satisfy the non-anticipation assumption. We have no information about future outcomes when we place our current bet. So with that clarified, let's go back to the main objective, defining stochastic integrals in continuous time. First, let's find a continuous analog of the process W. In a discrete setting, the process W is called a random walk. We define the symmetric simple random walk, Wn, where n equals to 0, 1, 2, and so on, as Wn is the sum from I equals 1 to n delta Wi, for n equals to 1, 2, and so on, and we define separately that W0 is 0. And here's a sample path of the simple random walk. At each step, it either goes up or down by 1 unit. And we can quickly deduce some basic properties of the random walk. First, the mean of Wn is 0, because the average of each step is 0. The variance of Wn is n times the variance of each step, which is equal to n. The variance of delta Wi is 1. So the key observation here is that the variance is linear in time. And next up, because Yn is a sum of IID random variables, by the central limit theorem, if n is large, Wn approximately follows the normal distribution. So Wn is approximately a normal 0n random variable for large n. And with these observations, we can construct the continuous analog of Wn, called the Brownian motion. So a Brownian motion is a continuous time stochastic process that takes also continuous values. Without getting into the technical details, the Brownian motion is, in a sense, a limit of random walk, in which the step sizes in time and space satisfy a very special scaling property. And here's the sample path. It looks rather rough, a characteristic which we'll get back to. And the Brownian motion was first observed in nature by the botanist Robert Brown in the middle of the 19th century. Its mathematical formulation, however, came much later. And speaking of which, this is the definition. The standard Brownian motion, or Wiener process, is a continuous time, real-valued stochastic process, Wt, t greater or equal to 0, with the following properties. First, we have W0 equals to 0. It starts from 0. Next, Wt has continuous sample paths with probability 1. That is to say, the trajectories are almost always continuous. Next, Wt has stationary, normally distributed increments. For s greater or equal to 0 less than t, the increment Wt minus Ws over the time interval s to t follows a normal distribution with 0 mean and a variance of t minus s, that is the length of the time interval. We say that the increments are stationary because their distribution only depends on the length of the time interval, not its starting point. So if we have two equal length time interval starting from different time, the increments over each of these time intervals are identically distributed. That's why it's called stationary. And lastly, Wt also has independent increments. If we have two non-overlapping time intervals, s1 to t1 and s2 to t2, the increments over those two time intervals are statistically independent. So these are the defining properties of a Brownian motion, which are inspired by the random walk in discrete time. From the definition, we can show that the Brownian motion is nowhere differentiable. So it turns out that continuous but nowhere differentiable functions are not just mathematical pathologies. They arise in nature. We can attempt to calculate the derivative of Wt, delta Wt over delta t. The numerator from the definition is a normal random variable with 0 mean and a variance of delta t. So divide that by delta t, we get another normal random variable with 0 mean, but with variance of 1 over delta t. As we can see, as delta t goes to 0, the variance blows up. It means that the derivative is not an L2 random variable. So we say, in the L2 sense, that the derivative of the Brownian motion does not exist. And this non-differentiability turns out to have some major ramifications. It calls for a new type of calculus, as we shall see in future videos. That is, new chain rule, new product rules, and so on. And now we're ready to define the Ito integral. So consider a time interval, say from 0 to t. We first divide it into n subintervals, each one with length delta t, that is t over n. And the endpoints of the subintervals are ti. I ranges from 0 to n. So ti is I times delta t equals I times t over n. And the stochastic integral from 0 to t of the function xs with respect to the increments of the Brownian motion dws is defined as the limit as n tends to infinity, the sum from I equals to 1 to n, x at ti minus 1 times wti minus wti minus 1 quantity. So looking at the summand, the function x is evaluated at the left endpoint ti minus 1, and it gets multiplied by the increment of the Brownian motion in that time period. And to simplify the notation, we just write x of ti minus 1 as xi minus 1, and the increment of the Brownian motion as delta wi. This is not to be confused with the random walk, in which wi is only plus or minus 1. Here, delta wi can take continuous values. And we reiterate that the definition uses the left Riemann sum. Once again, this is to respect the non-anticipation assumption. Let's go over the diagram once again. So we have the time interval, partition it into n subintervals. At the I subinterval, we evaluate the function x at the left endpoint, multiply that by the increment of the Brownian motion over that subinterval, and do that for each subinterval and sum up all the contributions. And that's the definition of the Ito integral. And here we have a visualization of the definition. This is the function x, and here we have the Brownian motion. First, let's partition the time interval in the graph of x. Evaluate x at all the left endpoints. Notice that we don't even need the value of x at the final endpoint. And then we partition the time interval on the graph for the Brownian motion. And in each subinterval, we calculate the increments, delta w1, delta w2, and so on. And then we just calculate the weighted sum and take the limit. The integral from 0 to t, xs dws, is defined as the limit n goes to infinity of the sum I from 1 to n, xi minus 1 times delta wi. It all looks well and good, but we shall say something about the meaning of the limit here. There are various notions of stochastic convergence, but here we're using the notion of mean square convergence, also known as L2 convergence. A sequence xn of random variables is said to converge to another random variable xi in the mean square sense if for each n, xn has finite second moment, also xi has finite second moment, and lastly, the most important condition, the expectation of xn minus xi absolute value squared tends to 0. So here, because we're talking about the limit of an expectation, this is just the limit of a sequence of real numbers, which we all understand from basic calculus. Borrowing the language of the L2 geometry, this is in fact a distance function. It says that the L2 distance between the sequence xn and xi tends to 0. And we call xi the limit in the mean, or the mean square limit of xn. And here are some common notations. We can write xn converges to xi with an L2 on top of the arrow, or we can put a dot after each letter in the limit, L dot I dot M dot xn equals to xi. This stands for the limit in the mean. So with this notion of mean square convergence, we can now write the definition of the Ito integral more precisely. We define yt, the stochastic integral, as the limit in the mean of the sum. And this is to say, the L2 distance between the random variable and the sum tends to 0 as n tends to infinity. As we can imagine, rigorous proofs of integrability is not a trivial matter. And by integrability, we of course mean that the random variable yt actually exists. And doing such proofs require measure theoretic probability, which we would avoid almost entirely in this series. Why? Because I'm a YouTuber greedy for views. If we go full-blown measure theory, people might get scared away. At the very end, let's do a simple example. Let's integrate a deterministic function. Let's take yt to be the integral from 0 to t f of s dws, where f of s is a deterministic function in time. It does not care about the history of W or any random process. It just places a predetermined bet at a specific time. It only depends on time. And of course, by definition, this is the limit in the mean square sense of the sum. I ranges from 1 to n, fi minus 1 delta wi. First, let's look at a trivial case where f is a constant. In that case, the sum simply telescopes. Namely, the sum simply collapses to wtn minus w naught. And of course, wtn is the final endpoint, and w naught is 0. So we just get the limit of cwt. And this is independent of n, so it's equal to cwt. This is completely trivial. Next up, let's look at the non-constant case. In such situation, yt generally has no closed formula, but still we can talk about the distribution of yt. Remember, delta wi is a Gaussian random variable. And fi minus 1, these are just constant. So the sum for yt is just a linear combination of Gaussian random variables, which is of course also Gaussian. And to fully specify the distribution of a Gaussian random variable, we just need its mean and variance. So let's first calculate the mean, which turns out to be just 0, because the mean of each delta wi is 0. Next, the variance of yt. Since delta wi's are IID, the variance of the sum is just the sum of the variance, and the scaling factor fi minus 1 needs to be squared. So the variance of yt is the limit of the sum of fi minus 1 squared times the variance of delta wi. By the definition, the variance of delta wi equals to the sub-time interval, which is delta t. So we have the limit of the sum fi minus 1 squared times delta t. But this is just a regular Riemann integral from calculus 1. So that's just the regular Riemann integral of the deterministic function f of s squared ds. So to summarize, our first formula in stochastic calculus, the Ito integral from 0 to t c dws is cwt. And next, let's integrate the exponential function e to the theta s, where theta is a constant. And by our formulas, this is a normal random variable with 0 mean, and the variance of the integral of e to the theta s squared, that is e to the 2 theta s ds. And of course, evaluating the integral is elementary. So this is the result. Even though there is no closed form formula for the second integral, its distribution has a closed form. It's a 0 mean Gaussian with variance e to the 2 theta t minus 1 over 2 theta. That's it for today's video. Thank you very much for watching, and I'll see you next time. Bye.